going and verify that it is actually streaming. So let's see. Okay, you see it. It says live. Excellent connection. You guys are my witness. It's supposed to be working. We'll see. All right. So homework 2 is underway. I sent you a note last Friday, I think, realizing that we haven't talked about the very last model that you need to be able to estimate in homework 2. And I have a general policy of trying to have at least a week in between when we finish covering something and when I expect the homework due. And so for that reason, I pushed it back into next week. So it is not due on Thursday. But homework 3 is also available. That's where you get a chance to practice CFA on your own data. So if you are looking for things to do, I would recommend getting started on that as well. Oh, thank you for the celebration icon. Yes, procrastinators rejoice. You have a few more days. But you can currently do all but like 4 questions. So the bulk of it is available on things that we've covered. So are there any questions on homework while I'm on the topic? Let me get my chat window here just in case folks want to communicate that way, which is fine. Okay, Kayla, did you have a question or did you just unmute yourself randomly?
Oh, I guess that was random. Sorry.
Okay. Well, it puts like a green box around you, like, it gets an exogenous attention cue. So that's why I caught you. Plus, you're right in the middle of my Brady Bunch boxes. I have one. Can you say more about this question? What is the sign difference between the model CFI and a perfect CFI? Yes, I can say. So what I'm looking for with the keyword sign difference is what is CFI supposed to be? And relative to that, how much higher or lower is the CFI value for your model? So if you have the right CFI, you might not be entering the right sign for it because I intend it to convey that as well, direction relative to expectation. Okay. All right. Other questions? What formula do we need to get question 9 and 10? Is that the question about alpha and inter-item correlation? Yes. Okay, so alpha is available from your output, and then there is a formula inside lecture 3. Let me see if I can find that real quick. Oh, nope, that's example 3, my bad. Things always open very slowly whenever I have the stream going, but I'll see if I can find it real quick. 1 second. Here, slide 21. Given alpha, you should be able to use the equation to figure out what the average inter-item correlation is. And so I just did that in a calculator. So this will be one of the very few hand calculations requested of you. Next question for CFI, is absolute fit considered 1? Yes. So CFI is the one that is bounded between 0 and 1, where 1 is best and 0 is worst. TLI is also in that same metric, but it's unbounded. You can actually have a TLI above 1 or below 0. But the standards for what is considered good fit, 0.95-ish, are the same in both measures. Okay, close out of those. All right, other questions? No? All right, well, shoot me an email if you come up with any because there is no class on Thursday. I will be attending a conference. Whatever aspects of lecture 4 and example 4 that we don't get through in class today, I will make a video to finish that up so that we can start on a new topic next week. Lecture 5 and example 5 are posted for you. We are going to be transitioning from the world of CFA into IRT, item response theory. and its factor analytic cousin, item factor analysis. So starting with binary responses and then eventually transitioning into ordinal responses and other kinds, fitting latent trait models for those as well. So I am starting then on slide 62. This is the process by which you can conduct likelihood ratio tests to see if changes that you've made to the model significantly change its fit. So most of the time you will be able to test changes to your model as nested model comparisons, meaning like if you add something, what is the improvement to the model fit from adding a parameter? Or if you take a parameter away, what is the decrease in model fit that results from estimating the simpler constrained model? And the formula for the likelihood ratio test is more complex than usual because of the robust correction scaling factors that have to be incorporated into the formula. So the formula is here. And just to remind you, inside the Excel spreadsheet that goes with example 4, there is a tab called MLR Comparisons Table 2, where I have built a spreadsheet that does those calculations for you. So you can use this to be able to enter your own model fit statistics if you need to compare nested models when you're doing this in homework 2 as well as homework 3. And just to review, the parts that are in yellow are the parts that you fill in, and then the parts that are in blue here get calculated as a result. So your test statistic is shown here. That's in chi-square terminology, the degrees of freedom, so the number of parameters added or removed, and then the p-value that goes with that test statistic are calculated in the last 3 columns here. For those of you who like to see calculations to help you understand how things work, I'm one of those people too, like I like to be able to see if I can figure out how all these parameters and stuff work together. I wanted to point out that I've also done that for you in other tabs. So for instance, in the tab for single factor models, I have the values for the standardized solution and how they were calculated, as well as from the original factor solution, so you can see how all of these things go together, as well as how the model predicts what the covariances between the items are supposed to be. So we have the original data covariance matrix, for instance, and the model predicted covariance matrix, which I have formulas in here that are pulling the model parameters and showing you how that actually works out. These are the things that are computed for you in M+, but it can be instructive to actually see the computations yourself, as well as the difference between the model predicted correlation matrix and the one from the data here using my favorite heat map coloring system. I did the same thing for the 2-factor models that we ended up with, and the rest of this is stuff that we haven't yet talked about. So they'll be part of reporting statistics for this example. All right, so you will be tasked in homework 3 with evaluating the fit of your model. So we've got global fit, right? That's one thing we're looking at. And that is an overall picture of how far off your model predicted covariances are from the ones in the data. So it's really talking about the match between the covariances and the factor loadings and factor covariances that are designed to mimic those covariances, the correspondence between the two. In models in which each item gets an estimated intercept, all the means will be perfectly accounted for, and if each item gets its own error variance, then all the item variances will be perfectly accounted for. So it boils down to covariances versus loadings and factor covariances. So we talked about the idea of testing improvements in model fit. So if you add something, the chi-square test, you want it to show that the model fit has improved. So the model gets taller after you add something. If the chi-square test for the change in height is significant, you would say that the model fit has significantly improved. It got better. If the chi-square test after adding something is non-significant, you would say that it's not better. It's backwards in terms of what you would talk about if it's a larger model being compared to a more parsimonious smaller model. So for instance, if you start with a 2-factor model and it looks like the 2 factors are almost perfectly correlated, then you might want to test whether you can simplify the model and just have one factor instead. And then if you have a significant chi-square test for that kind of comparison, you would be saying that the model got worse. So if you go from two factors to one factor, that change in fit means that the model got worse. If the change in fit is non-significant, then the model is not worse, meaning you could get away with the simpler model. So just in talking about it, make sure that you're clear what you're trying to do. Are you trying to make it better by adding things, or are you trying to make it fit not worse by simplifying? And keep in mind that AIC and BIC, those indices that go along with your log likelihood height, those are in smaller is better form. So they're already multiplied by -2, and they can be used to talk about non-nested models. So when would that come up? It's not very frequent, but let's say that you have a two-factor model and you're not sure whether or not a given item should load on factor 1 or whether it should load on factor 2. You could fit each of those models. They will have the same degrees of freedom, and they'll be non-nested. But you could look at AIC and BIC to see which one is preferred, where smaller is better in that case. If you wanted to have an item that already loads on factor 1 and test if it should also load on factor 2, like to have two loadings for a single item, that's what's known as a cross-loading when you let it load on an additional factor, and that would be a nested model comparison because you're directly testing that additional extra factor loading. And you get a test of its significance right there in the output, so you technically wouldn't even need to do a likelihood ratio test in that case. Keep in mind that models with different outcomes are not comparable. So if you decide to remove an item from your model, you cannot do a likelihood ratio test to make some sort of statement about whether that hurt the model or not, because the height of the data is reflective of the amount of the data. And so your heights are going to go down if you have less data going in, say if you use 7 indicators instead of 8. So we can't compare nested models, any kind of comparison, non-nested or nested, if you change the data. So just keep that in mind. Those models are not comparable. We talked about that as well. So when you're expanding the model, how do you know whether or not how do you know how to change your model? The question is, if you have a model that doesn't appear to fit well, and even if you do, you want to go through this process of looking at local fit, right? Do you remember what local fit is? Looking at everyone's smiling faces and hoping someone nods. Real people, you're on the hook for this? Yes. Real faces, I should say, not the faces. Yes, yellow thumbs work too. Local fit, that's the idea of going piece by piece, every single pairwise combination of covariances and seeing how far off they are. That can help you diagnose where the misfit is coming from. You will get an index of residual correlation that takes the form of a z-score. Those are known as normalized residuals, where if you have large positive values, that indicates that your two items want to be more together than what the model says. They have a higher correlation in the data than what is predicted by the model. If you have negative values for your normalized residuals, that means they don't want to be as together as they are. So they might want to be on separate factors, for instance. So you can go through this list and decide from a combined, what are the data saying, what is my theory about these items and the content of the items say, and decide on a solution for how you might change a misfitting model. One of the things that it will tell you to do in the Voodoo modification indices to solve extra correlation between two items is to add an error covariance. So to do that, such as in homework 2, you would list the name of the item, the word with, and then the other item that you want the covariance to be between. And if those items are considered outcomes by the model, you will be adding an error covariance. And if the items are predictors, it would just be a regular covariance. But what you're doing in adding an error covariance is introducing additional multidimensionality. So this is where I think we were left off after lecture on Thursday, looking at this picture. Does this look familiar? Okay, so we'll pick up there. So if you have a situation in which two items are more related to each other than what your single factor model would predict. So this is an example from your textbook looking at items measuring general social anxiety, and he found that even though all 6 items are supposed to measure one factor in common, 2 of the items look like they have something else in common besides the factor. And so this would show up as a positive normalized residual. The idea that the correlation between these items in the data is higher than what the model says it should be. There's something else there in common. So what that something else is, we don't know, but how you represent it has a lot of possibilities. So the most direct way would be this middle picture with an error covariance. You could also split those 2 items that are more related into their own factor, and then the extra relationship happens because they have loadings that are on that one specific factor relative to the other one. Or you could take a higher order approach, which is down here, in which that single correlation between the 2 factors is given a name as a general order factor. And the one on the right here, this is what's known as a method factor. It's also known as a bifactor model in the IRT world, but you can fit bifactor models in a CFA framework. This is allowing a separate factor that induces the error covariance. And so the separate factor is not related to the first factor because these 2 items still have a loading on the first factor. So it's a different viewpoint than just a 2-factor model. So would this be where subscales come in? A question from the audience. Yes, it would. So a subscale kind of model would be consistent with the left side here, where we would have 2 different aspects of anxiety, but they would be thought to be indicators themselves of a globe, like the total score, sort of the overall construct. And if you only have 2, that's not enough, right? Do you remember how many items you need for a model to be testable and estimable? 3 is testable, or excuse me, 3 is estimable, 4 is testable. If you only have 2, then you can't actually test if the 2 subscales are indicators of a higher order trait. That model isn't even identified. The only way to make it identified is to fix the 2 loadings to be equal to each other. So if you're thinking of sort of clumps of items as measuring something and the somethings they're measuring are related, that would lend itself to the pictures on the left here. If you just want to account for that extra relationship but not interpret it, not think about it, just sort of set it to the side, then that intention corresponds to either an error covariance right here or the factor analog. So the idea that you would set up a specific factor just for those 2 items that allows an additional correlation. So even though these pictures look the same, what's happening on the right here is that all 6 items are still loading onto the one factor to begin with. The 2 items that have the error covariance get an extra factor. And it turns out that when we switch to models for categorical data, when we are predicting binary or ordinal outcomes, those outcomes, when we use full information maximum likelihood, do not have a residual variance that's estimated. Do you guys remember logistic regression? Have you seen that before? What's the error variance in logistic regression? If you don't remember this, we're going over it next week. It's 3.29 in logistic regression and it's 1 in probit regression. It's a constant that's not estimated. Well, it turns out that if you don't have an estimated residual variance, you can't have an estimated residual covariance either. So in IRT world, you can't have error covariances if you don't have residual variances. You got to do this thing instead. So putting in a method factor is a factor-based way of putting in an error covariance. But this strategy is sort of like, yeah, I don't care why these 2 other items are related. I'm just going to put something in my model to fix it and then move on and talk about it as if it's one-dimensional still. Whereas the strategies on the left here are going to take whatever those two items have in common and make it more of a focus, give that their own factor that could in turn be related to other things. So there's not necessarily a right way or a wrong way to modify your model, but the idea is to do so in a way that is theoretically defensible and matches your intention with what you then want to do. So there's a lot of gray area in what would be acceptable. But I just want to point out that these are all mathematically equivalent ways of handling two items that have more in common than what the factor predicts. All right, when might you simplify? Well, if you have multiple factors in your model and they're super highly correlated. I think the cutoff of 0.85-ish is given in your textbook if memory serves. That's where that came from. But certainly factors that are super highly correlated might indicate that it's really just one thing in common. And so this is a situation in which you could do a nested model comparison and test whether or not multiple factors could be condensed into one if they're super highly correlated. When might you drop an item? If it doesn't have a significant factor loading. So if you have a factor loading that is 0 or not differentiable than 0, it is not helping you. Likewise, if you have a factor loading that's negative, it's actually backwards. And that shouldn't happen in a situation in which you've already coded your variables such that higher scores mean more of the trait. So, Lexi, did you have a question or did you just accidentally unmute yourself? Waiting. Maybe the latter. Okay. Yeah, I notice when you guys unmute yourself because then it like does the green around your box, it calls attention to you. So as I said earlier, getting rid of an item may be one potential way to deal with multiple unpredicted covariances. So if you go through your row of the normalized residual and there's one item that seems to have a problem with everything else, getting rid of that item is one way to help the misfit of your model. But you want to be careful in dropping items because every time you drop an item, you're potentially dropping your reliability. So dropping items is not a general strategy unless you really have so many that reliability would be fine without it. If you have an item that is nearly the same thing as another item, if it's redundant, so if the items have a correlation themselves above, say, 0.9 or whatever, then you kind of only need one and you don't necessarily need the other. So there's a few situations in which dropping things might make sense. Just keep in mind that you can't do model comparisons to verify the utility of that strategy. So what I'm looking to see from you guys then in when you try this on your own data, I'm not looking for you to make your model fit no matter what. That's not what I want. I want to see that you know how to interpret the information that the factor analysis results is giving you, and that you can apply the lens of both what did the data want and what makes sense to decide what to do about it. If you're looking at your model and you're not sure what to do about it, ask me. You don't have to figure this out all by yourselves. Ask each other. We can figure it out together because there's not necessarily a straightforward right answer. It may not always make sense to go from one factor to two factors, for instance. There may be situations in which the right path is not clear. So I'll help you if that is the situation you're in. Okay. Questions or thoughts about model revision? We have a question. Let me see. What is number of missing data patterns in the output? Is that just how M plus indicates there is missing data? Yes. So it is tracking the number of permutations of I've got this variable but not this one. I've got that variable but not that one that exist in your data. The more missing data you have, the harder it will be for things to converge. Do we need to do anything with that? No. No. These models are assuming any missing data is missing at random, which means conditionally random after factoring in the data that you do have for them. That's not a testable assumption, but there's nothing that needs to be done differently if you have missing data. All right, other questions? Okay, So what happens if you get no numbers? You may see sometimes an error message that has the words not positive definite in it. That means your model is broken and you can't keep it. So if you see those words, that means that the factor analytic solution has come up with something that is not supposed to be there. It has decided, for instance, that your most likely value for your error variance is a negative number. Can't have negative variances. It might decide that in the standardized solution, the most likely value for the correlation between factors is a value above 1. Can't have it. So you will need to scan your output right before the numbers. There will be a message. If it says anything like non-positive definite, proceed with caution. If your model doesn't converge, you will know that because you will get a column of estimates with no standard errors or anything else. It will just give you where it left off in trying to find the heights. And so that's an indication that your model may not be identified, for instance. In terms of troubleshooting, make sure that you've obeyed the rules of identification. So every factor needs to have a mean and a variance. You can either set the mean to 0 or you can set an intercept to 0 and estimate the mean. For the variance, you can either fix the factor variance to 1 or you can estimate or you can fix a factor loading to 1 and estimate the factor variance instead. I'm asking you in your homework to use the fix it to 0, 1 strategy. That way you know what a unit is in terms of your factor. It's just a simplification in terms of interpretation. Watch out for locally under-identified factors. So looking back, say at, let me find this picture again. The picture up on the left here, the public speaking anxiety that only has 2 items, that factor is locally under-identified. If it was all by itself, that model would not be estimable. Because there are the other variables in the model and it has additional information it can borrow, it would technically be able to have 2 different loadings here. But if the model blows up, that would be the first thing I'd check. Even though it could be possible, it may not be possible with your data, and you may have to fix these 2 loadings to be equal to each other to get the thing to work. Another question. When we're exporting data to a CSV, do the variables need to be ordered in a specific way to write the names? It needs to match, but other than that, it doesn't have to be in a certain order. M+, when you list out the names of the variables, doesn't know what they used to be called. So as long as you get the right order of the columns in your listing of names, like you could simplify greatly. Like you could call the first, ID, if that's what your ID variable is, and then say, item 1, item 2, item 3, even if they used to have other names, if that's what it is. So yes, it doesn't know what they used to be called, and you can use that to your advantage. So long as you don't duplicate variable names. If you're going to have more than one subscale, then naming everything item is not going to be sufficient. So the same rules would typically apply in data sets. Another question, could you use the factor plus the method of addressing multidimensionality if you only had 2 items on the factor?
I was just checking that, like, if you had that problem where you only had those 2 items, could you do it that way if you wanted to, like, have 2 separate factors and you didn't just want to look at, like, error covariance?
Can you have 2 factors if there's more than 2 items?
If we had that problem where, like, you saw two of the items had a strongly related error covariance, and then you were like, oh, it's under that factor's under identified, that situation you were just describing. In order to solve that problem, could you use that method plus or factor plus method factor?
I don't think so, if I follow you. You can't do both at the same time because they would both be trying to solve the same problem.
Could you switch to the second one?
Sure, you can do anything you want. So in the method factor on the right here, what makes this work is that both loadings are held equal. So this is the identification problem has been solved, and that has to be the case for this thing to work because they still have their loadings on the original factor.
So if you were going to use that, you'd have to be okay with the two loadings being the same.
Yes.
Okay.
By the way, the loadings being held equal to 1 is a way to induce a positive error covariance through a factor. But if the error covariance were negative, you would have to fix one of the loadings to 1 and the other to -1 to create a negative error covariance. So we'll be talking about that more in the context of IRT, in which you have to use the strategy rather than the error covariance option. But conceptually, this extra factor is the same thing as an error covariance with a name on it. It's doing the exact same thing. And you could have more than two. If you had 3 items that all had something in common, you could load them onto their own specific factor and fix all of the loadings equal or not. In that case, you would have the choice. Okay, does that help, Andrea? Yeah, okay. All right. Other questions on strategies? Okay, and let's get into this. So this idea that you can take the information that you get from the process of estimating the model, you get diagnostics as to where it is wrong, and then you can use that information to change the model. We're using confirmatory factor analysis in an exploratory way. Like, I'll be the first to admit that, right? It's not the case that you can only fit one model, and if it doesn't fit, you're done. You can change the model. Ideally, if you have to settle on a different structure than what you had intended, you would want to collect another sample and try out your revised structure on that another sample to make sure that it's not just a fluke of one sample that's causing you to change what your model is. But this idea that the information you get from the analysis is diagnostic is why you don't ever need to do an exploratory factor analysis. Because all you have to do to get started with a CFA is have a clue. Fit a single factor model. The local fit will tell you where the problems are. It will tell you which items want to be more related than what the model says and which items want to be less related. And you can use that information. Okay, well, if these items want to be together and these items want to be together, let's do a two-factor model. Let's see how that goes. So there's no reason to go all the way back to the drawing board with exploratory, where everything loads on every factor, so you have no idea what it means. I also posted for Thursday, for those of you who want a more mathematical justification for why EFA sucks, I have posted 2 lecture videos and slides to go with it from a previous class taught by Jonathan Templin at the University of Kansas, where he goes into the mathematical details as to why he hates EFA. So if you want to have the background, there you have it. It's 2 long videos, but I know for some of you that's something that may come up when you have to defend your choices. So I want you to have that additional ammunition. The constraints that happen within EFA to make the model identified are crazy. The same constraints that we're using to make the model identified are theoretically interpretable. And so that's why the confirmatory approach is preferred. All right. So we've talked about fit. But we're not done yet. Once we have a decently fitting model, the next question, okay, so how well is our factor measured? That is a completely separate issue than whether or not the model fits. So to illustrate why these things are completely different, consider 2 different kinds of item correlation matrices here. I can have a matrix of items that are all correlated 0.1, and I can have a matrix of items that are all correlated 0.8. And a single factor model will describe each of these matrices perfectly. They will each fit perfect. But arguably, if my items on the left here have almost nothing in common, there is no point of doing a factor analysis. Like, what we're doing in factor analysis is taking what the items have in common and giving that a name and putting it in a circle. Like, that's what a latent trait is the covariance gets a name and we call it, depression or forgiveness or, resource scarcity or something, right? We call it a name, but it's covariance that we're naming. There has to be covariance or game over. So I had this question once from another faculty member who was well acquainted with CFA, and she brought me a factor solution where she had almost perfect fit, but the factor loadings were non-significant. And she was confused as to how to interpret this. So what do you think I told her? How can you have a perfectly fitting model with non-significant factor loadings? Game over? Yes. How did you know? It's like you've been listening to my catchphrases. I think I may have been slightly more polite because she was senior faculty and I wasn't tenured. But yeah, game over. How can you have a non-significant factor loadings in a model that fits perfectly? What does perfect fit mean? It means that you have accurately captured the pattern of covariance across your indicators, whatever that is. It does not say that there is covariance worth capturing. So is covariance worth capturing is pointing towards reliability. How much of the variability in these items is attributable to their standing on the factor and how much is something else? So if I take these correlations and square them, right, a correlation of 0.1 becomes 0.01. It's 99% something else. The model can accurately capture that, but it's not then useful. And yes, game over in that case. So we're looking at the solution itself. We want to make sure that everything is in line. All of the standardized loadings are between 0 and 1. If there's negative loadings, then that shouldn't have happened at this stage. We want to make sure all the error variances are positive numbers. We want to make sure that all correlations between the factors are within the boundaries of -1 and 1. All of that good stuff. We also want to consider how well the linear model actually functions in predicting outcomes. So let me give you an example. This is a sample item from data that were collected to try and be as continuous as possible. It was a rating scale where the subjects moved a slider bar between 2 points to say to the extent to which they agreed with the sentence. So in theory, like this works really well because then you have all this potential variability. You're not just like forcing them to choose 1 or 2 or 3. But what do you do with a variable that looks like this? It turns out that if you fit a linear model to a variable that looks like this, here's what happens. So the predicted item response is on the y-axis of this plot, and the factor scores are on the x-axis. So remember, factor is your predictor, the item response is your outcome. Well, this is just a straightforward single predictor regression model. I've got the intercept for each item, and I've got a slope for each item, and I can make a regression line for each item. And what you want to see in thinking about whether or not a CFA is appropriate is that the predicted item responses stay within the range they're supposed to. And what happens here is that as soon as we cross a factor score of about 0.1, the line of predicted response goes out of bounds. I can't have a score of 120. It only goes up to 100. So even if the model looks like it fits well, is the model the right model has to do with whether or not a line is a reasonable thing. In this case, not so much. Unfortunately, what to do instead is not as well developed. If this were an ordinal scale, I would know what to do with that, but this histogram is not showing you all the continuous values that underlie these bars, right? This is a truly continuous variable. There's not a ready-made measurement model that goes with that. So one thing that I thought to do was to do what's known as a logit transform. So it's the same logic as what's used in logistic regression, except that I'm changing the data rather than changing the model predicted mean. So if I do that, I then have a linear model that predicts the logit of the response. And when I back translate that predicted logit into the original scale, it creates this sort of S-shaped curve that obeys the boundaries. So this type of transformation is one way to rescue a variable that a linear model simply isn't appropriate for if there's not a ready alternative available. For data that are ordinal, though, there is a ready alternative available, and that's what we would do instead. But just because it's continuous doesn't mean that a linear model is going to work. So making these kind of plots is one of the things I'm going to ask you to do in homework 3 to look at your data to decide whether or not CFA is okay enough. Because there were quite a few of you who had scales with, say, 5 options or 7 options where they looked reasonably symmetric, and so you thought CFA might be okay. Well, here's another way to determine if CFA might be okay. Does the model predicted outcome stay within the range it's supposed to at prototypical levels of the factor? Ideally, you'd want to see the predicted outcome stay within the range for at least 2 standard deviations on either side. So you'd catch about 95% of your sample within the predicted range. That's not going to happen here. So assuming that a linear model is reasonable, assuming that all of your parameter estimates are within the boundaries they're supposed to be, we can calculate a reliability using the solution. So I'd like to introduce you to our new friend omega. Omega is the model-based version of alpha, where rather than assuming that all of the items have equal discrimination and that they all have independent errors, the extent to which that is not true goes into the formula. So we could calculate how much information is inside each item, which is a concept that's coming in more detail in the following weeks. Here's the formula for which you can calculate information from a CFA model. It's the unstandardized factor loading squared over the error variance. This is not a thing in CFA though, because the standardized loadings give you exactly the same information. So how much variability in an item is due to the factor is functionally the same thing as information, and so we don't ever see this. But that idea is the basis of this thing omega. So the formula for omega, if you look at the chunks of it, the numerator has to do with how much information is due to the factor, and the denominator has that plus how much information is due to error. So it looks like your classical true score definition of reliability. It's signal over total. But there's more nuance in here. We have the variance of the factor times the sum of the loadings squared. So because we're letting the loadings go into the formula, we're not assuming the items are all equal. We're not assuming equal item discrimination. Any differences in how good one item is relative to another goes into the formula as the loadings. Likewise, any differences in how much error variance is included in an item goes into the formula. And the last thing here on the bottom right, twice the sum of any error covariances is what that means. Because if you have, if it goes back to the definition of what kind of variance would be in a sum. If the things you're summing are independent, then their total variance just comes from their variances. But if the things you're summing are dependent, then the covariances show up in there too. And so if you're in a situation where you've measured one factor plus some stuff, right, you have an error covariance in there, that's actually going to count against you. It goes into the denominator, but not the numerator. So in most cases, if you have a positive covariance, then that would make it harder to have a good reliability coefficient. So omega is the reliability of the sum score according to the model. Later in the course, we'll get into the reliability of the factor score as a separate concept with a separate estimate, but this is reliability of the sum score. So this is what you give your reviewers instead of alpha. You give them omega. And because omega still assumes unidimensionality, which we would have tested, if you have more than one factor, you have more than one omega. So there's my summary of that. Do you want to see how to get omega out of your output? Why not? You can make M plus do the math for you. So this formula, right, I could plug this into Excel. And in fact, I did. There's a tab for that. Omega is the very last tab. I calculated omega, and that gives me the point estimate. But one of the nice benefits of asking M plus to do this math for you, besides not having to enter all the numbers into a calculator, is that you get a standard error for it too. So let me show you how to get that. So I'm picking up in example 4 on page 12. So just to recall, in this example, we're dealing with 6 items that were initially all thought to measure forgiveness of situations. After looking at the fit of the one-factor model, which was not good, it looked like from the local fit information, it was not good because the items that were worded the same way wanted to be more together than the items that were worded differently. So I split the 2 items into 2 factors, and we found in looking at this stuff last week that those 2 factors seemed to better account for the pattern of covariance and did a good job fitting the model, fitting the data as a whole. So to make M plus do math, can you all see this with me? So the syntax that is shown here is similar to what we've had up to this point. So sit p by is defining my latent factor. So sit p is my name for it. You would want to give your own name for it, 8 characters or fewer. And what variables are being measured by the factor, which variables are measuring the factor, I should say, then are the ones that have the stars here. So the stars are referring to their factor loadings being estimated. Now the new part here is in parentheses. The terms in parentheses are either going to be labels or they're going to be constraints. If you list a label for as many parameters are in that physical line of code, then it's just a label. So for instance, I have 3 factor loadings. I am labeling the first factor loading L1. The second loading is going to be L2, and the last one is L3. Likewise, for the negatively worded items factor, I am naming those L4, L5, and L6. Now, why am I doing that? Because what I want to do is to have M plus replace those internal labels with whatever the estimated parameter is to become. So down here, those labels are going to get used in a new command that you haven't seen yet. It's literally called new. It generates linear or nonlinear combinations of estimated parameters. So those of you who are familiar with Stata lincom and NLCom, that's this. Those of you who are familiar with SAS estimate statements, that's this. SPSS, it's called test statements, and I can never remember what it is in R, but there is a version of this in R too. So we're asking for linear or nonlinear combinations of model parameters. So model constraint is what it's called to get this thing started. That is a general command. It will not turn blue. It won't. New is where we are listing a name for the new linear combination that we are going to create. So I'm creating 2 things right here, omega p and omega n, one for the positive factor, one for the negative factor. So omega p, the numerator of it is the sum of the loadings for the indicators on the positive factor squared. So what goes in the parentheses here, instead of the actual numbers that the loadings turned out to be, I'm using the labels. So L1 is going to become whatever the loading for 1 actually was. It's a placeholder. L2 is going to become the number that the second factor loading was estimated to be. And star star 2 is how you do a squared term in M plus. And the one out front refers to the factor variance. So the formula for omega is the factor variance times the sum of the loadings squared. That goes into the denominator as well, and then the sum of the error variances. So E1, E2, and E3 come from right here, the line where I asked for each item to get its own error variance, and I gave them the names E1, E2, and E3. Does that make sense so far? Okay. Omega n works the same, just with a different set of labels. And because there are no error covariances, I don't have that extra part of the formula, but that would go here. 2 times any of the error covariances if I had any go in the denominator. For completeness, I've labeled all of the parameters in here, even though I'm not using all of them in doing further math. So you don't have to label everything, I chose to. But this is one of the things that you will get a chance to practice, having M plus do math for you using estimated parameters. And so then the output that results gives you the list of new parameters. So omega for the positive factor was 0.744, and omega for the negative factor is 0.775, and we have the standard errors that go with those as well. So for a conventional value of reliability, these are like, right? I wish they were 0.8, but they're not. So even though our model fits well, I don't have great reliability for each of my latent factors because they only have 3 items. Any guesses as to how I could get better reliability? While you're pondering that question, so would the same type of code be used to give values for hypothetical people to have a value on a certain item? Yes. So for instance, you could compute the predicted item response for a factor score of 2 by labeling things and asking for that as a new parameter. Yes, you could. But any guesses as to how I could get a higher omega reliability coefficient?
Didn't you say something about having negative covariances would affect this value? Maybe I am remembering that wrong.
If I had error covariances between the items, that would count against me. That would make omega lower if they're positive error covariances. It would make it higher if they're negative. But assuming that I don't need any error covariances, what could I do to make my reliability better? Yeah, 1 vote for add more items. Yes. 3 is not enough. So my model is identified, my model is estimable, my model is testable. I tested the fit and it's good, but I have so-so reliability because I've got 3 items for each factor. And because omega is a unidimensional idea, I can't lump them together. There are people who've come up with omegas for multidimensional solutions. To me, they're weird and unnecessary. But there are adaptations to this that you can use to describe, say, higher order factors and stuff like that. But each of my factors right now is not greatly reliable. Okay. So what does that mean in terms of factor scores? So other things that you're going to get out of your output is describing the characteristics of M plus's best guess as to what their factor scores are for each person. So if you remember from our little brief journey into estimation, I don't need to know what the factor score is for each person to estimate this model. Its factor scores per person are not model parameters. Their variances, means, and covariances are. But I can ask for M plus to generate what the most likely factor score is for each person. We'll talk more about these in the context of IRT, but these are EAP estimates, expected a posteriori estimates. You can think of them as if each person has a possible distribution for what their factor is, these are the means of those distributions. But more than just the means, we want to know what the standard errors are. We want to know how unreliable each person's factor score potentially is. And so the sample statistics for estimated factor scores, they give you the standard error for each of the factors. And in these models, because reliability is constant across the trait, so is the standard error. So if you think about standard error of measurement here, standard error of measurement is 0.4. So let's put a confidence interval around any one score. Let's say if I had a factor score of 0, my confidence interval would go all the way to minus 1.7-ish, all the way to positive 1.7. Like 4 standard deviations of people is what my standard error of measurement would be. So like somewhere on the number line, that's your factor score. So an omega reliability of 0.7 something translates into a standard error that is huge. So these factor scores are kind of garbage. Like if I were to output this score and try to make decisions about someone's life, I would be in a world of hurt because the error around these factor scores is almost the entire standard deviation of the sample. The other thing I want to point out is the variability of the factor scores. That's what these numbers here are telling you. So what is the variance of my factor scores supposed to be according to the model? Do you remember? We fixed it to something when we identified the model. What's the variance of my factors supposed to be? 1. Yeah. What did it turn out to be? 0.77 and 0.82. So the variability of what it thinks the most likely factor score is for each person is almost always going to be smaller than the variability according to the model. The term for this is called shrinkage. And it's why you do not want to output factor scores and stick them in another model if you can help it. You want to leave them in the model. If I had research questions related to how situation forgiveness predicted other things, I could answer those questions by leaving the latent factors in the model and estimating relations, correlations, or regressions with those other things directly. That's what SEM is for. That's where we're eventually headed. But because that last step is so relatively trivial, just getting the factors built itself is what we're focusing on to start with. So yeah, these factor scores are kind of garbage. 3 items is not enough, even though the items themselves are okay. Here's the distribution of the factor scores. Note that they each are showing a ceiling effect. There is a value over which no person gets a higher possible factor score. And that is a direct result of the fact that those people answered 7 for all 3 items, and that's all I know about them. So even though the factor scores are supposed to have a multivariate normal distribution in theory, in practice, that's going to be constrained by the information that's in your items. So other question, so what happens if the items are not enough and you need to use them in your model but can't ignore them? Do you use the item by itself? Using each of the items by itself would result in more error than using the latent factor. So you still want to use the latent factor. The point that I'm trying to make is that there's a big difference between trying to think about how the latent factor as a construct relates to other things, putting factor scores, and trusting those scores as if they're perfectly reliable. These scores are basically garbage because the error around them is so high, but they're still better than nothing. The idea would be to leave them as part of the model rather than output them. So we have truncated factor scores that have shrinkage relative to the variance they're supposed to. They have ceiling effects. These are the pictures that I made to test the idea of whether or not a linear model is appropriate. So this is a seven option set of items. So in theory, that should work. However, you can see that after a factor score of about 2, the predicted item response goes out of bounds. So I've drawn in the black dotted lines to show you where the bounds of the scale are. So even though there's 7 options, whether or not these are normal enough for CFA, these pictures would suggest that CFA is not appropriate. Not because they're not normal, but because a linear model predicting this ordinal response doesn't understand that you can't go past 7. And what if we had taken the mean? What if I just fit an add shit up model and I didn't do any of this? Well, the factor score that I would get is correlated almost perfectly with the mean. And this is why I think it is a very common practice once people have established a factor score to just go ahead and add shit up, because the end result of that process is often not very differentiable. The pattern of covariance between the factor scores and between the item means, though, is a little bit different. The factor scores are more related than the item means are, in part because they're estimated in a joint model for all of the items simultaneously. So that's going to push the covariance to be a little bit higher. All right. So this chart that I'm going to ask you to do in homework 3 was created in the spreadsheet that I gave you called Factor Model Predictions, where you can enter in, it goes so fast and then it doesn't want to, things in yellow, and everything else will be calculated for you. So I'm trying to help with the calculation side of things to get a sense of what these regression lines would look like. But it's not any different than what you learned how to do in simple linear regression, because it's one predictor per outcome. All right. Questions on any of that? Okay, one last piece then. Finally getting to the end of your homework. What if we had used alpha instead of omega? How wrong would we be? There's an empirical answer to that question. The difference between the two is that alpha assumes items are equally discriminating, and omega doesn't. Omega has the factor loadings in the formula. It doesn't assume anything other than unidimensionality, which we've figured out was true after we have 2 different factors, each of which is unidimensional. Whether or not the items are equally discriminating is a testable hypothesis. So let me show you how to do that so that you can do it on your homework. So I'm fitting the same factor model. This is on page 14. But I'm illustrating another use of the parentheses. This is not a label, this is a constraint. So in parentheses, rather than having, L4, L5, L6 for the 3 loadings, I have one word. It's called neg load. That stands for the loadings on the negative factor. The things in parentheses can only be 8 characters or fewer. What I have done is instruct the model to force all 3 items, situations 1, 3, and 5's loadings to be equal to each other. So this is a tau equivalent or true score equivalent or equal discrimination model. In 2 weeks, this will be called a Roche model. Dun, dun, dun. Planting that seed for you. The idea that whether or not each item needs its own discrimination, its own loading, is a testable hypothesis. So this is a situation in which we started with a model where we had all 3 loadings be separate, and now we're fitting a simplified model where we're forcing all 3 loadings to be the same number. Why do I not make the positive loadings be equal? Stay tuned, because I wanted to focus on each factor individually for this example. There's a reason. So here's what happened. A joint loading for all 3 items was estimated at 1.254. So the question we have to answer is, did forcing those 3 loadings to be the same make the model fit worse? Because when you take things away, it's worse or not worse. To answer that question, that's a likelihood ratio test. So here is a comparison of those 2 models. The log likelihood from the model that had all 3 loadings separate is the second one. The model where all 3 loadings are forced to be the same is the first. And the difference between the 2 models is a chi-square of 35 on 2 degrees of freedom, which is significant, which means worse, which means that these 3 loadings do not want to be the same number. They don't like it. Note that the standardized loadings are still different. That's because we haven't also forced the error variances to be the same. The standardized loadings reflect not just the factor loadings, but the amount of error in each item. So the standardized loadings can still differ because we let the errors differ. So here's a comparison then of the fit of those 2 models. The one that has 2 fewer parameters, so going from 3 loadings to 1 loading, fits significantly worse. Now here's the positive factor. So I took the constraint off of the negative one, since I know that that didn't work, and I put positive loading as a constraint on the positive factor. So now the 3 positively worded items loadings are being held equal. And by the way, just demonstrating, if the loadings are in fact equal, then alpha is omega. So the difference between the 2 boils down to whether or not you've allowed differential loadings, since there's no error covariances in the model. So we check the difference in fit right here. 2 degrees of freedom, chi-square of 2.5. So because the result is non-significant, that means we made the model not worse. Meaning that we could let all 3 positively worded items have the same loading, and it's fine with that. So now we've cut down 2 parameters, simplifying the model. The very last step is also constraining the error variances to be all the same. So we're adding a constraint to the line that has the error variances as well as the line that has the loadings. And I note that if this model holds, then the Spearman-Brown index of reliability is valid. So this idea that you have equal loadings and equal